Okay, we're going to have a look at the next thing in differentiation, and that's differentiating inverse trigonometric functions. So let's have a look first of all what I mean by an inverse trigonometric function. It's the button on your calculator when you look at it that looks, it's got a sine or a cos or a tan, and it's got a -1 up here. This is the inverse trigonometric function. So let's have a look at an example. So say we have sine of x is equal to y. Well, then I can rearrange that equation and I can write it sine inverse. This is called sine inverse of y is equal to x. So let's fill in a few numbers and I'll show you exactly what I mean. So say if we have sine of 30 degrees. Well, sine of 30 degrees is equal to a half, 0.5. But I could work backwards. I could say sine inverse of 0.5 is equal to 30 degrees. So if you take your calculator and if you press sine of 30 degrees on it, you'll get 0.5. But then if you work backwards and you go sine inverse of 0.5, you'll get back to 30 degrees. And this function here, that's called an inverse trigonometric function. An inverse trigonometric function. Okay, so let's have a look at a few of the rules that we have already. So we have a few of the rules for differentiating. So we've learned how to differentiate something that looks like x to the power of n, something that looks like ax to the power of n. A constant differentiates to give us 0. Sine x. So these are trigonometric functions. So when I differentiate sine x, I get cos x. When I differentiate cos x, I get minus sine x. And when I differentiate tan x, I get sec squared x. So they're all the rules that we've had before. And I'm going to give you three more now. Three more rules that allow us to differentiate inverse trigonometric functions. So say, again, I know you look at this first of all and it looks maybe a little bit scary, but it's actually not. It's very straightforward. So say we want to differentiate something that looks like cos inverse x over a. And remember, anytime you see an a in this table, it just means a constant. It's just a number. So a could be 3 or 4 or whatever. So if I want to differentiate cos inverse x over a, when I differentiate that, I just get this fraction over here, this quotient, -1 all over the square root of a squared minus x squared. So we'll do a few examples in a minute and you'll see exactly what we mean. If you want to differentiate sine inverse x over a, when I differentiate that, I'll get 1 all over the square root of a squared minus x squared. And then the third one, if I want to differentiate tan inverse x over a, I will get, there's no square root this time, I'll just get a all over a squared plus x squared. So let's have a look at a few examples of differentiating using that. So say we have these questions. We want to differentiate the following. So the first one, we just have to differentiate sine inverse x over 3. So let's say f of x is the first one. F of x is equal to sine inverse x over 3. Well, that looks, we go back to our rules that I just gave you. Sine inverse x over 3 is just exactly like this one. So, but instead of an a, we have a 3. So when I differentiate sine inverse x over 3, I will get 1 all over the square root of 3 squared minus x squared. So anywhere there's an a, I just fill in 3 because we're differentiating sine inverse x over 3. So sine inverse x over 3, if f of x is that, then f dash of x will just be 1 all over the square root of 3 squared minus x squared. I can tidy that up. 3 squared is 9. So I get 1 all over the square root of 9 minus x squared. So very, very straightforward. The second one then, we have to differentiate cos inverse. So we'll write, say, g of x is equal to cos inverse x over 4. So the rule for cos inverse, we go back here. When I differentiate cos inverse x over a, I get -1 all over the square root of a squared minus x squared. So when I differentiate cos inverse x over 4, I get -1 over the square root of 4 squared minus x squared. So very straightforward. So g dash x will equal -1 all over the square root of 4 squared minus x squared. And then 4 squared is 16, so I get -1 all over the square root of 16 minus x squared. So again, very straightforward. If we want to differentiate, say, the third one, tan inverse x over a. So let's use a different notation here. Let's say y is equal to tan inverse x over 5. So we want to differentiate that. Well, the rule for tan inverse goes like this. Tan inverse x over a differentiates to give us this. So tan inverse x over 5 will differentiate to give us 5 all over 5 squared plus x squared. So here we'll have dy over dx, because we're using this notation. Dy over dx will be 5 all over 5 squared plus x squared, or that's 5 all over 5 squared is 25 plus x squared. So again, very straightforward. And then the last one, we have to differentiate sine inverse x. Now this one looks a little bit different to the previous sine function, or inverse trigonometric function with sine in it that we differentiated up here. In that up here we had x over 3, here we just have x. But this x, well, I can rewrite that as x over 1. You can always put anything over 1. So when I'm differentiating this one, so I have, let's say, y is equal to sine inverse x. I'm going to rewrite that as sine inverse x over 1. Because now I can just use this rule that we have here. Sine inverse x over 1 will differentiate to give us 1 all over the square root of 1 squared minus x squared. So here I have dy over dx will equal 1 all over, what is it, the square root of 1 squared minus x squared. And 1 squared is 1, so I'll just be left with 1 all over the square root of 1 minus x squared. So very, very straightforward. In the next video, we're going to have a look at slightly more complicated ones where you might have to use the chain rule in the middle of, as well as the inverse trigonometric function rule.